Everybody, wanted to spend a little bit of time talking about vapor pressure. This is going to lead into a little bit of colligative property stuff in terms of vapor pressure lowering. But before we talk about that, we need to know what vapor pressure is. So vapor pressure, I guess we should start off discuss what a vapor is. And so a vapor is a gas of some sort of compound that is normally found usually in the liquid state. I guess you could have solid vapors too, like sodium vapor, light bulbs and things like that. But typically it is a gas that we normally find as a liquid in normal conditions, normal settings. And so, like this illustration here provides, what you have is you have particles of a liquid that will spontaneously, all on their own accord, jump out into the gas phase because they have space to move. Now notice it's not like this particle way down here. It's always particles near the surface that will jump out into the vapor phase or the gas phase. And there will also be other particles that will come back into the liquid phase. And so when you have particles moving around, they apply a pressure. And that pressure is the pressure of those particles moving from the gas phase or to the liquid phase to the gas phase is what we call vapor pressure. Okay, the pressure that's being exerted upwards on this little interface between the gas and the liquid. This is where we get the phrase volatility from. Okay, and so volatility, the more volatile something is, the higher the vapor pressure. So the more molecules that are going to jump off into the gas state. Another thing that is kind of interesting is that smells. That is a direct cause of vapor pressure, of things jumping into the gas state, going and traveling to somebody's nose, and us smelling them. Okay, and so the higher the vapor pressure, the more likely it is that we are going to smell something. And so that's kind of an interesting side. And so when you have a liquid just sitting out, what ends up happening is most of the time it reaches kind of a balance or an equilibrium between the atmospheric pressure, which is all around pushing down on everything, and the vapor pressure, which is pushing out as the molecules are jumping out into the atmosphere. And so atmospheric pressure and vapor pressure are typically balanced when we do this. Now, as we heat something up, molecules move more. When they move more, they jump out into the vapor phase more often, and therefore the vapor pressure will increase and cause more gases to form, and that's why things evaporate, is because the vapor pressure increases compared to the atmospheric pressure. So if there's more vapor pressure, we're talking about more particles jumping out into the vapor phase, okay, the gas phase. If there's less vapor pressure, that means that this is the particles aren't jumping out as much into the vapor phase. Okay, I use the word jumping. They're not actually jumping. I'm anthropomorphizing. I'm making them human or animalistic. But when the vapor pressure is lower, there's less of them jumping out into the vapor phase, into the gas phase, and so therefore they're less likely to smell things. There's less possibility of particles to travel all around. And in order to calculate things, in order to calculate vapor pressure, you use the ideal gas law. It's kind of straightforward. But instead of using the properties of the whole gas, we're going to use the properties of the vapor that we're dealing with. So if we're dealing with water vapor, we're going to have, this is going to be not the pressure of the water, but it's going to be the vapor pressure of the water, and the volume that the vapor is going to fill, and the number of moles, and then the temperature of the vapor. Okay. Now, I say tables here because there are lists and lists and lists of tables, and this happens to be the vapor pressure of water, and I don't think I would ever expect you to memorize vapor pressures of anything. You just have to go to a table and look it up. Okay, and so here's the interesting thing. Notice that here, the vapor pressure of water at 100 degrees C is 760 millimeters of mercury. That's interesting because what is standard pressure? Standard pressure, as in STP, standard pressure is 760 millimeters of mercury. That's equal to 1 atmosphere. And so when something boils, okay, this is where it gets fun. When something boils, that's where the vapor pressure, boiling, is when the vapor pressure equals the atmospheric pressure. What happens as we go up mountains in like Denver, Colorado? We have the Mile High City. Here it is. Hi. Okay. Well, the atmospheric pressure goes down. Okay. And so if the atmospheric pressure goes down, that means that the boiling point of something will go down, and that is a colligative property. Okay. So we're talking, what if the atmospheric pressure now is only 633.9? Well, that means that water is going to boil at 95 degrees Celsius and not 100 degrees Celsius. So there are these tables, and that's just an interesting little side note about boiling point and vapor pressure. But let's go here. Okay, so let's do a sample problem. So let's say you have 2 liters of water. 2 liters of water in a room, and then you seal up the room. Okay, now this is a totally ridiculous example because you have to make sure that the room is completely sealed, no holes, windows not open, no crack under the door, that sort of stuff, but whatever. Okay, get over that part. And so we're going to seal up the room, and we're going to see if we're going to have the water evaporate. Okay, and so it says, is all the water going to evaporate? So this is a comparison question. When you're given a comparison question, what you want to do is you want to calculate how much will evaporate and compare it to how much you have. Okay, and so notice we're given a density and the vapor pressure. Okay, so the vapor pressure, so that's the P. So what I'm going to do is I'm going to symbolize that with P sub V, vapor pressure, and that is equal to 23.8 millimeters of mercury. The volume in the room, the volume that the vapor is going to fill up, is going to be, so that volume is about this, 4.25 times 10 to the third. Now you can write that as 4.25 times 10 to the third liters, or if you want to write that in not scientific notation, that's 4,250 liters, whatever you want. Okay, you seal the room, wait for it to evaporate. Will all the water evaporate when it's at 25 degrees C? So the temperature is 25 degrees Celsius. And what we want to calculate is N, how much, the number of moles. Okay, while the R is still the same, 0.0821 liter atmosphere per mole Kelvin. And now we convert, then calculate. That is always going to be my thing. Convert, then calculate. So this, we have to convert to ATM. The standard unit for pressure is ATM. So we X-line. We know that 1 ATM equals 760 millimeters of mercury. Okay, so we're going to go 23.8 divided by 760. And so we get a pressure of 0.0313. This is already in our correct units. Now this has to be in Kelvin, so that's add 273. So this is 298 Kelvin. Now at this point, it is just a it's just a plug and chug. Okay, so plug and chug. So PV equals nRT. So I'm going to take some of these things and erase them. Okay, because I already know, so I'm going to go here. Okay. So I already have it all figured out. So it's PV equals nRT. Our pressure is 0.0313. Our volume is 4,250. That equals N, which is what we're trying to solve for. Okay, now I can erase the rest of this just to get room. And then R is 0.0821. And then temperature is 298. Okay, so we go 0. So I think it's best if we just carry that number through. We don't have to do anything other than just multiply it. So we're gonna. So let's see here. So I'm going to bring up my calculator. Okay, you can see the conversion that I did previously. Sorry that it wasn't up before. So we're going to take that converted pressure and multiply by the volume. And now we're going to take and we're going to divide by this, right? So divided by 0.0821. Then we're going to divide again by 298. And so that means that the number of moles equals 5.44 moles of water. That's how much water is going to fill the room. Okay? So we have to figure out how much water is that. Okay. Because now we're comparing 2 liters versus 5.44 moles. So we have to convert to get them into the same units. So we can either convert moles, we can go moles to grams to milliliters to liters, or we can go liters to milliliters to grams to moles. Or we can meet somewhere in the middle. But the point is with a comparison problem like this, we need to make sure that we're comparing the same units. So it doesn't really matter. So I'm going to take this value that I just calculated, and I'm going to convert that to liters. So we take this, we have 5.44 moles, and then we X-line it. So for every 1 mole, water has a mass of 18 grams. So we take that, we go times 18, okay, and so we get 97.9 grams. And so now 97.9 grams, and we're going to X-line this. So to go from grams to milliliters, it's not a gas, it's a liquid, so we have to use the density. That's where this comes in. So this is grams milliliters. So this is 0.997 grams for every 1 milliliter. So we take that, we divide that by 0.997, and so we get 98 milliliters, or which also equals, move the decimal point over, 0.098 liters, which is definitely less than the 2 liters that we started with. So are we going to fill the whole room with water vapor? Absolutely. There's plenty there to do that. So that is your sample problem on how to apply water vapor, how to apply vapor pressure and what it means. And so have a great day.